Hello everyone, welcome to my YouTube channel. I am Harshita from Sri Venkateshwara College of Engineering. In this video, let us discuss about applications of vector space and the linear transformation. Introduction. Vector space or mathematical structure that consists of vectors and operations such as addition and scalar multiplication. Vector space are used in linear algebra to study and analyze system of linear equation and transformation. A vector space must satisfy certain axioms such as a closure under addition and a scalar multiplication and presence of an additive identity and inverse. And the next is linear transformation. A linear transformation is a function that preserves the vector space structure, meaning it maps vectors from one vector space to another while preserving addition and scalar multiplication. Linear transformation can be represented by matrix or by a system of linear equations. Linear transformation can be used to solve system of linear equation, find eigenvectors and eigenvalues, and analyze geometric transformations. And let us discuss about the applications of vector space and the linear transformation. Vector space and linear transformation are used in various fields such as physics, computer graphics, and data analysis. In physics, vector spaces are used to model physical quantities like force, velocity, and electric fields. In computer graphics, linear transformation are used to perform operations like rotation, scaling, and translation on objects in a 3D space. In computer science, vector space are used in machine learning, algorithm for data analysis, and pattern recognition. And the next, let us discuss detail about the application of a vector space and linear transformation. The first is image processing. Image processing using vector spaces and linear transformation involves presenting images as vectors and applying linear transformation to manipulate them. In this approach, each megapixel intensity values can be treated as vector components. Linear transformation like scaling, rotation, and translation can be applied using matrix, enabling operation like resizing, rotation, and image enhancement. This technique provides a mathematical framework for various image processing tasks, offering efficient and flexible ways to modify and analyze images. And the next application is a signal processing. Signal processing involves manipulation and analysis signals often using the mathematical concepts like a vector space and a linear transformation. These transformations help extract, modify, or analyze signal characteristics, contributing to application in communication, audio, image processing, and more. Linear transformation like Fourier transfer convert signals from the time domain to the frequency domain. By analyzing the transformer signal in the vector space, various signal processing tasks such as noise removal and filtering can be performed. And the next is data analysis. Vector space are utilized to present and analysis data in various fields such as finance, biology, and social science. Linear transformation help in dimensionality reduction techniques like a principal component analysis and the singular value decomposition. By applying linear transformation, high-dimensional data can be visualized and interpreted in a lower dimensional space. In data analysis, vectors are used to present data points and linear transformation can be used for data reprocessing. Principal component analysis is an example of technique that uses linear transformation to extract important features from the data. And the next is physics. Vector space and linear transformation play a crucial role in physics by providing the mathematical framework to describe and analyze various physical phenomena. In physics, a vector space is a collection of vectors that can be added together and scaled by constant. These vectors can be represent quantities like position, velocity, force, and more. Linear transformation or mathematical operation that preserves vector addition and scalar multiplication. In physics, these transformations are used to describe how physical quantities change under different conditions. For example, in classical mechanics, linear transformation can repeat rotation, translation, and scaling of coordinates. And the next come robotics. Vector space and linear transformation are fundamental in robotics and control system. Robot movements can be represented as vectors in vector space, and linear transformation are used to control these movements. By applying linear transformation, robots can navigate, manipulate objects, and perform complex tasks automatically. And the next is machine learning. Vector spaces and linear transformation are expensively employed in machine learning algorithms. Linear transformations like matrix multiplication help in feature extraction, dimensionality reduction, and model training. Vector spaces are used to represent and analyze data in various domains such as text, images, and numerical data. Support vector machines is an example of machine learning algorithm that uses linear transformation to find an optical hyperplane or for classification. And the next is image compression. Vector space and linear transformation are employed in image compression algorithms like a JPEG. The image is divided into blocks, each represents as a vector in vector space. Linear transformations such as discrete cosine transfer are used to compromise and decompromise the image by reducing redundancy. And the next is electrical engineering. Vector spaces are used to analyze electrical signals and circuits. Linear transformation help to describe the behavior of electronic components and system. Application include designing communication system, analyzing power grids, and developing audio processing algorithms. And the next is cryptography and coding theory. Vector space are used to represent encryption and decryption algorithm. Linear transformation help ensure secure communication and protect sensitive information. Application include secure online transaction, encrypted messaging, and password protection. Error detection and correction techniques highly rely on linear transformation in coding theory. And the next is network analysis and graphic theory. Graphs can be represented as adjacency matrix which form vector space. Linear transformation can be used to analyze network properties such as connectivity and centrality. Vector space and linear transformation enable the study of complex networks in the fields like social network analysis and transportation planning. And the next is computer graphics. Vector space are used to represent the geographic objects in a computer graphics. Linear transformations such as rotation and translation are applied to create realistic 3D scenes. Linear algebra is essential for rendering, animation, and stimulation in a computer graphic. Application include video game development, special effects in movies, and virtual reality simulations. And finally, I conclude that vector space and linear transformation are fundamental concepts in mathematics. Their application extend across various fields including maths, data analysis, cryptography, quantum mechanics, network analysis, differential equation, image processing, computer graphics, and more. Understanding vector space and linear transformation ensures our ability to model and solve complex problems in these domains. Thank you for watching this video.